Hi, in this video I will discuss about few questions from last year Jest exam, and first I'll start with a very common problem from quantum mechanics which is actually asked in a lot of competitive exams as well as in PhD interviews. So this is the problem. So I'll read the question. A quantum particle of mass m in a 1D harmonic potential of form this, which is a harmonic simple harmonic potential, but there is a little difference from the usual textbook harmonic potential that whatever the harmonic potential that we usually encounter in a textbook. Here if I look at the limit, so it is, this potential is for x greater than 0, but if x is less than 0, this potential becomes infinite. So this is the difference from the usual harmonic potentials that we have encountered in the textbook. So for this potential, we need to figure out which is the correct wave function, ground state wave function out of this 4, which is the correct ground state wave function out of this 4 wave function. So let's start the solution. So first quickly revisit the normal harmonic potential and their energy eigenstates and eigenvalues. So this is the usual harmonic potential looks like. And these are the different energy energy eigenstates, and energy eigenvalues are E0, so these are the energy eigenvalues, and how the energy eigenfunctions looks like. For 0 it looks like a Gaussian wave function. This is psi 0 of x. Next one, is how it looks like. Psi 3 of x. So this we know. This is the harmonic potential wave function, different wave function, and different energy level. Now, one key point here is that when the n is odd, 0 and 2, the wave function is actually has certain value at the center. As you can see, for n even, the wave function is not going to 0. That's the point. But for n odd, wave function goes to 0 at the center, or x is equal to 0. So this is the message or the point that is useful for this problem. So this is very clear. For n is equal to 0 or 2 or even, the wave function is not going to 0 at the center, but for odd, wave function is always going to 0 at the center, x is equal to 0. So that's the point. Now I will draw this potential I am drawing. So this is how, as a function of x, it moves. There is 0, infinity, this is x direction, this is also x direction, and this is how the potentials looks like. This is the infinite value. V is infinity, in this side for x less than 0. So So now the point is that what are the wave functions for this potential? So first thing is that this is not extended from in this form. So this is actually there is a sharp, there is a boundary. After that the potential is infinite. After this x less than 0, the potential is infinite. So the wave function now cannot extend in the x. The wave function cannot extend in the negative x direction, and the wave function should go to 0 at x is equal to 0. Sorry for this handwriting. The wave function go to 0, x is equal to 0, because this is the boundary. At the boundary, the wave function must vanish. Now, if I go to the harmonic potential, which wave functions are going to 0 at x is equal to 0? This one and this one. These are not going to 0. So, whether this wave function will not survive here, or this is not surviving, is the incorrect word. So, these are not the wave functions for this particular potential. So, we will start with n is equal to 1. So my first wave function, this will not the correct wave function for this, because it is not going to 0 at the center. So my ground state wave function becomes this one. So this is my ground state wave function for this case, and the ground state energy value is, and what is my first excited state? This is not, sorry, let's not create any confusion. So this is also not the first excited state, because the wave function is not vanishing at 0. This will become my first excited state. So only the wave function has this. So our shape of the wave function is like this. So these are my first and ground state wave function, and so on. If I draw, just take those odd wave function from this one. So this will become the wave functions for this particular potential form. This is very simple. Well, one can very quickly understand it. So when it becomes half harmonic, the wave function must go to 0 at the center, and this for n is equal to even, those wave functions are not going to 0, only these wave functions are going to 0. So this is one just intuitive way to check which wave functions are will survive or exist for this particular potential. Other way is just do it very rigorously, solve the Schrodinger equation. So we are not doing this. We are just from this one we are just able to intuitively guess what are the wave functions that will exist for this potential. And as a also you can see here, this is the ground state energy, and here the ground state energy becomes 3/2. So all the odd n is equal to odd wave functions and energy eigenvalues will exist for this potential. So now if I look at the answer, so this will be the correct answer. This is wrong because psi is going to 0 at x, psi is not going to 0 at x equal to 0, so this is wrong. This is also wrong. This is the correct wave function, but this is not the ground state. This is the first excited state, and this is the ground state wave function. So I hope you can understand or got the intuition how we have solved this problem instead of doing or solving rigorously the Schrodinger equation. So if you have any doubt, you can just write your doubt in the comment section. And now we will move to another problem from the exam, from the last year Jest exam. So let's move to the second problem. So here this is a problem of 3.5 system. Usually these problems you will encounter mostly in Jest exam. So for a 3.5 particle placed in a magnetic field B the Hamiltonian is this. So I'll just write the Hamiltonian. That's the most important thing. So this is my Hamiltonian. So the key point here is this Hamiltonian is minus omega, which is some frequency, and this is the SY operator. So we know SY operator has eigenvalues of plus h bar and minus h bar, plus h bar by 2 minus h bar by 2. These are the eigenvalues, and corresponding eigenvectors are, I'll just write, these are the corresponding eigenvectors. So this is the when the spin is along negative y direction, and this is along the positive y direction. These are the corresponding eigenvalues. And one thing is very clear, that without solving it, we can directly guess that since this Hamiltonian is nothing but omega times Sy, so its eigenvalue will be just omega times the eigenvalues of Sy. So what will be the eigenvalues? And corresponding eigenvectors are up and down. These are the corresponding eigenvectors or states. Here extra minus will come because of this minus sign, and it gets plus. So this is my Hamiltonian eigenvalue, and this is eigenstate, eigenvalue, and eigenstate. Fine. Now, so we have all the information about the Hamiltonian now. So now the initial state means at time t is equal to 0, initial state is this, which is the eigenstate of Sz operator. So if Sz acts on this, it gives you, and Sz. So these are nothing but the eigenstates of Sz, which means the state means the spin is pointing along the positive z and this is negative z, and these are the corresponding eigenvalues, and the initial state is at the positive Sz. Now, if here I am not deriving it, one can basically easily connect the eigenstates of Sy is actually expressed as a linear superposition of eigenstates of Sz. So this is how one can write this eigenstate of Sy as a superposition of Sz. As we know, this eigenstates forms a complete basis, and any state can be written in that basis. So I am just writing this up state in the Sz basis in terms of plus and minus. Similarly, I can write this down state in this form. Now, my goal is to express this psi 0 in terms of the eigenstates of Hamiltonian. So for that, I just need to write this psi 0 in terms of up and down. So how to? For that, I need to express this plus in the form of up and down. So it is very easy. If I just take sum of these two, then I will get this plus as a so I can write this plus, since these two since these two form a basis, so I am writing this as z spin in the basis of in this Sy spin basis. So in this form, this at time t is equal to 0. So let's now look at the question again. So at time t is equal to 0, this is the state. What happens? At a later time t, if I measure S, what is the probability of getting minus h bar by 2? What is the minus h bar by 2? So what is the possibility of getting this? So question is, what is the possibility of getting this one at time t? So this is our question, and so let's figure out what happens to a wave function with time. This is very simple. Since I have expressed the wave function in the basis, in the eigenbasis, so this up and down states are nothing but the eigenstates of Hamiltonian. So they just multiplied by this phase factor, undergoes free evolution. So multiplied by the phase factor, this one is just I am writing for the convenience, E1 and E2. So E1 is the energy eigenvalue of up and E2 is the energy eigenvalue of down. So this is my question. So here just I am writing what is E1. E1, if H x1 up, it gives E1 up. So E1 is this. Similarly E2. So if I just write it, plus will come and here a minus. So this is my state at time t. Now what is the probability of getting minus? So now if I want to find this probability, in minus state, I need to take a projection of this minus on this psi of t and mod square. This will make 1 by 2 and so this is the thing. Now if I project minus state on up, it gives me I by root 2, and minus state on down, it gives me minus I by root 2. So I by root 2 I will take common since I absolute, so it will become 1 by 4 and it will become I omega t by 2 minus minus I omega t by 2 as a square, and at the end it becomes so this is it. There is a possibility of finding it in the minus state. So I'll just revisit this problem quickly. So this is our Hamiltonian, and we know that Hamiltonian contains Sy, so the eigenvalues are just simply the eigenvalues of Sy multiplied by this omega, and eigenstates are eigenstates of Sy, so up and down. And next we know our initial state is eigenstate of Sz, and we just express this in terms of energy eigenstates up and down. And next we write psi, we just do the free time evolution since these are the energy eigenstates, so these will be simply multiplied by this factor E1 and E2. So I'll get this is my at time t. Next I did just simple this is the final probability that I want to figure out. So I just projected this minus with psi t, takes the square, and in simple algebra I'll get this sine square multiplied by 2. So I hope you will get this problem. If you have any doubt, you can just send your doubt in the comment section or write it down in the comment section. Now next, let's move to the next problem. So let's move to the next problem. So it's a very interesting problem. I'll read this question. Consider a quantum particle in the 1D box. Wow, this is our favorite topic, 1D box. 1D box. This is our one-dimensional box of length L. Fantastic. Length L. Now it states that the coordinate of the leftmost wall of the box is that x is equal to 0, so it extends from x is equal to 0, and rightmost wall is that x is equal to L. So L. So we are familiar with everything, and the particle is in the ground state at t is equal to 0. So this is the problem of 1D box in the ground state, which is very well known to us. We know the wave function as well, we know each and everything about this. That's the best thing. Now there is a twist. At t is equal to 0, we suddenly change the length of the box to 3L by moving the right wall. So this suddenly change is a very important word in this question. Now this is the box. Now if I suddenly change this box to a length 3L, and as you can see, it's not happening at some later time t. It's happening at time t is equal to 0. So we are just instantaneously changing the length of the box, but in this process, whenever you see this suddenly, the wave function remains undisturbed. It means this box is now expanded to 0 to 3L, but in that process, the process happened so quickly, the wave function is not disturbed. So this is the wave function that the wave function remains its original state, this one, but now the box becomes 3L, and it is very clear that we expect. So it is very clear that this is not the ground state of a box of length 3L. So what we expect? So we expect this is a 0 to 3L box. This is the ground state. This is the first excited state, like that. But in this 0 to 3L box, this wave function is actually in the previous ground state, and the new ground state and excited states look like this. But this is the psi of x, and this is the state of the right now. This is the state of the particle or the wave function of the particle in this 3L box. Not these are, because the change happened so suddenly that wave function doesn't change. It remains to its original location. So it is only 0 to L up to this, and these are the eigenfunction of eigenfunction or the wave function of a 0 to 3L box, and this is the original wave function, which is now due to a sudden expansion, which looks like this. Now we need to find what is the probability that the particle is in the ground state of the new probability of finding in the ground state. So this is the actual ground state of 3L, but the particle is in this state inside the 3L box. So we need to find what is the probability of finding this one in this wave function, kind of thing. Means I know it's little bit confusing. First we expand this box, but with the expansion it becomes very weird that I expand this box, it becomes 3L, but the wave function is not extending from 0 to 3L, it remains L, all because of this sudden expansion. So whenever you see some suddenly change or such kind of things, you feel that the box is expanding so quickly, but the wave function remains it's lazy to change. It remains the same. So 0 to L. Now this is my wave function and 0 to 3L is my system. So I need to find what is the probability of finding, suppose, this wave function. What is the probability of finding, so this phi of x? What is the probability of finding phi of x? What is phi of x? This is the ground state of 3L. Phi of x is over 2 by 3L sine of So I need to find this probability, which is very similar to, now it is similar to my earlier problem. So how to find this probability? Mod square will come, obviously. Now I need to take the projection of this wave function into this wave function, because this is the wave function of the particle inside this box. Now what is the possibility of this wave function to remain in this 0 state? So I need to take a projection of phi of x into this psi x. And what is the limit of the integration? This is very careful thing. So the limit of the integration should go from 0 to 3L, right? But no, it will not go from 0 to 3L. It will go from only to 0 to L, because our phi of psi of x is extending up to only 0 to L. So now this is the probability that we are looking for. So 4 by 3L will come out. And so this is the answer. Just evaluate this integral, you will get some number. I am lazy to figure it out now. So I'll just save the problem and go through it again. I know this is a little bit weird, but if you have any doubt, you can just write in the comment. I know this is a little bit weird problem. So consider a quantum particle in a 1D box of length L. The coordinates are given by 0 to L. This is the initial state of the particle, the ground state of a 1D box of length L. Now we suddenly change the length to 0 to 3L, but we change it so suddenly, the wave function is lazy to change itself. So the wave function remains in its original situation. But if I go to a box whose length is expanding from length is 0 to 3L, so in that new box it has new ground states, this, but the initial, since in that process the initial wave function doesn't change, so in the process the initial wave function is not changing. It is the in a 3L box, this is the wave function, and these are the different eigenfunctions of a 3L box. Now the question is that what is the possibility of the particle to remain in that ground state? So in this wave function, how much is the contribution coming from this ground state? What is the possibility that if the particle in this state, what is the possibility of finding it in the ground state? So one thing that I missed to explain in this solution, since you can think about these, so this is my new system of 0 to 3L, and the eigenfunctions of 0 to 3L are suppose given by phi n x. These are the eigenfunctions of this system. So all these eigenfunctions form a basis, correct? And I can think this psi of x, my initial wave function, is some arbitrary wave function which remains in its actual state. Now I can write any wave function in a given basis. I can expand any wave function in a given basis, correct? So I can always, this is the psi of x, my original one, and these are the phi n. These are the orthogonal modes or the wave functions or the eigenfunctions of this box which is going from 0 to 3L. So I can always write the psi of x in the eigenfunctions in the basis of these eigenfunctions phi and x. Right. So this is very clear. So this is my psi x, and these are the I can always write this psi x as superposition of all these wave functions. Now the question they are asking, what is the possibility of finding in the ground state? So what is the possibility that now Cn, so all this Cn is actually the contributions from each wave functions. So what is the possibility of finding in the ground state? Ground state means n is equal to 1, and what is the possibility of finding the ground state, which is given by C1 mod C1 square. So for that what I have done, I just took that phi this side, so I will write it phi 1, phi 1. So I just took that phi multiplied by that phi 1 x in this side and take the mod square, and from that I am calculating C1 square. So this is just this thing. So this is nothing but finding this coefficient at the end of the day, which I am writing in this fashion. So the key point here, whenever you see a sudden change or sudden expansion or this kind of problem, if it is not written here, the problem was in other cases they wrote it that wave function is undisturbed, but they didn't write it. That's why they use this sudden change. Whenever you find a sudden change, you assume that whatever the initial wave function that remains undisturbed, but the system has went through some change, and that new system, the wave function remains the earlier wave function, and we need to find the overlap of the earlier wave function with the new system ground state. So this is the overlap or the probability. Basically overlap, from the overlap we can find the probability. So this is the way we are doing it. So if you have any doubt on these three problems that we have discussed, please write those doubts in the comment section, and we can discuss that even more in there. So thanks for your attention. Next time we'll come up with some other problem from the Jest exam. So thanks for your attention.